So we spent some time together looking at measurements and the conventions for expressing them with proper units and carrying them through calculations with the appropriate number of significant figures. But that's not the big idea. We always want those ideas at the back of our mind, never in the front. What should be at the front of our mind is solving more complex problems, and that's what we're going to start to do now. Now, any way that you express your solution to a problem that is clear and logical and shows all your units will be good for me. Sometimes students ask me, how much work do I have to show? What I recommend is that you treat it as if you're writing the answer for someone who doesn't already know the answer, that you are teaching your reader with your solution. So you should write it clearly enough that a novice could follow your argument. However, I'm going to show you a strategy that you're going to love. It's called dimensional analysis, and it works on the basis of dimensions or units. Now, we already love units, and we would put units in our calculation anyway. But with this strategy, dimensional analysis, we use the units to see a strategy for solving the problem. So I'm going to start with an example. How many kilometers are in 3.60 centimeters? Some of you might be able to do this in your head, and that's fine. But I picked this simple of an example not so that we were concerned about finding the right number, but so that we could learn the steps to solve any problem. That's why I'm going to really recommend this dimensional analysis. If you learn this approach, you have a tool that you can use even in unfamiliar situations. So what I'm going to do is start by making a map. Do you have to make a map? No, but the more complex a problem is, the more useful you're going to find this strategy. And this is my own personal thing. It's not inherently part of dimensional analysis. I'll use maps for solving any kind of problem. So I'm going to ask myself, what's the question part of the question? And the question is, how many kilometers do I have? Oops, let's get that in red. So I'm going to start at the end. At the end of the road, at the end of my map, I'm going to want to know how many kilometers there are. And now I'm going to play a game that I call, what do I need to know that? I find it so much easier to start planning at the end of the problem. I don't know if you've solved mazes with a pencil. It is so much easier to start from the back, from the front. There are so many things you could do from the front, but going from the back keeps you focused. All right, so what I need to find how to do this is a conversion factor. I want to know some relationship involving kilometers and relating them to some other unit. Now, I could probably work out in my head how many centimeters were in a kilometer, but it seems so much simpler to just go with 1 kilometer equals 1,000 meters. So what that tells me is, because I know a conversion factor that relates kilometers and meters, I could find out how many kilometers I had if I knew how many meters. And that conversion factor will be the way that I do that from meters to kilometers. Now, am I back to what the data given in the question is? No, I don't know meters either. I know I'm starting with centimeters. So I'll put that at the start of my map. And I'm glad I'm getting a chance to show you that I don't have to know everything. I don't have to see this all in order. I'm just writing something down and connecting things as I go. So what I can see, the gap I have to fill here is from centimeters to meters. And if I knew either how many centimeters were in a meter or how many meters were in a centimeter, I could do that. I do know that there are 100 centimeters in a meter. And I hope you know that too. That's one of the conversion factors in SI that I expect that you know. Because the conversion factor has units of both centimeters and meters, that will let me make my jump from centimeters to meters in the first step, and I'm set to go. So now I'm ready to actually solve this problem, and the map is going to give me guidance and keep me focused through the whole process. There's only 2 steps in this map, but you can imagine if I get to a 5 or 6 step problem, this map is really going to help things stay straight in our heads. Okay, so the map says I'm going to start with centimeters. And on the next slide, oh, maybe didn't leave room for the next slide. Let me insert one. Whoops, that's not what I want it to do. There's a slide where I can solve that problem. The map said start with centimeters, and the question said I had 3.60 centimeters. All right, so how I go on is I'm going to multiply by a conversion factor. And this is the actual dimensional analysis part of the problem. Because 1 meter equals 100 centimeter, those 2 values have the same value. I'm going to put one of those numbers, either 100 centimeters or 1 meter, in the numerator and the other in the denominator. Because when I have equal values in the numerator and denominator of a fraction, then I know that value is 1. And I can multiply by the number 1 as many times as I like without changing the value. Now, which part do I put in numerator and which in the denominator? Units are my friends. I'm not going to worry about the numbers at first. The units go first. So I've got centimeters in the numerator over here. To cancel those out, I've got to put centimeters in the denominator. So that means it's the meters that go in the numerator. Once I see the units, I know what numbers to put in. 1 meter is 100 centimeters. And I'm going to work these units like I'm not the one that proposed it. Centimeters cancel centimeters in the denominator, and I am left with 0.0360 meters. Woohoo! That's what I wanted. At the intermediate stage of my calculation, I wanted to have meters, so now I'm at the midpoint on my map. So now my map tells me where to go in the next step. I want to get from meters to kilometers. So I can take the number of meters that I have, and I want to get how many kilometers. So again, I'm going to multiply by a conversion factor. I want to get rid of meters in the numerator, so those go in the denominator. And I want to get kilometers in the numerator, so those go there. Units go first. Don't let the numbers get in the way. Once I have the units, I can put in the numbers that go with them. 1 kilometer is 1,000 meters. And I'm going to work my units like I'm not the one that proposed them. Meters in the numerator cancels meters in the denominator, and I'm left with kilometers. Woohoo! Now, that doesn't guarantee I'm right, but it's sure better feeling than if the units hadn't worked out. Now, you can use your calculator. I don't need to for this one. Well, actually, yes, I did, but I got it in my notes here with me. 3.60 times 10 to the minus 5 kilometers. That's one way to do it. One step in your calculation for every arrow in your map. But when you get fluent, you might be able to do it all in one. So my map says start with the number of centimeters. Then it says get rid of centimeters to get meters. Now that I have meters, I can multiply by another conversion factor. I want to get rid of meters and get kilometers. And 1,000 meters is 1 kilometer. Meters in the numerator cancels meters in the denominator. Woohoo! Left with kilometers. Now this one is easier to do in my head, but you can have a calculator if you want one. Now we're not done. We always want to think about the sense of our answer. First reassuring thing is we got the right units, not because we wanted it to be those units, but because it really worked out that way. The other thing you want to do is check and see if the answer makes sense. we started with a very small distance in centimeters, so it doesn't surprise me that it's a very small number of kilometers. That makes sense as well. And finally, the icing on the cake, always at the back of our minds and never at the front, do we have the right significant figures? In the measured quantity, there were 3 significant figures. The trailing 0 is significant because there's a decimal point in the number. In other words, it was measured to the nearest hundredth of a centimeter. The conversion factors were by definition, so they have infinite significant figures. In other words, they have no uncertainty. So my answer should be to 3 significant figures. Good. Don't throw that 0 away. It is truly significant. Another thing I want to show you about significant figures is at the top of the slide, in the intermediate step, I also carried the correct number of significant figures. 3 significant figures gave me 3 significant figures. You can carry 3 significant figures, you can carry more significant figures. But if you had neglected to show that 0, you would have thrown the significant figure away, and I would get you for that. Once you lose significant figures, you can't get them back. So that's your first example with significant figures. And again, you might be able to figure that out in your head. It's the approach of working the conversion factors that I want you to get. It's the dimensional analysis we're learning here. So when you work on your assignment, focus on the approach using dimensional analysis. I don't care what numbers you get. I want to see your solutions. All right, let's work on some more examples. In every one, I'm going to show you a little bit of a new twist. But as always, if you can pause the video and do it before I get there, that gives you real confidence. If you own it, you get to keep it and you don't have to study it later. So maybe you want to pause and solve the top problem on this slide. All right, I'm ready to go. And I'm going to make a map. Do you always have to make a map? No, but it's a really good tool to have in your toolkit. So I'm going to ask myself, what's the question part of the question? I want to end up with meters, and I want to end up with seconds in the denominator. So let's see what I need to know that. What I'm starting with in the problem is not meters, but kilometers. So if I knew a conversion factor that told me either how many kilometers were in a meter, or how many meters were in a kilometer, I could do that in one step. I know that conversion factor. In the last example, I showed the conversion factors explicitly. For example, 1 kilometer equals 1,000 meters. You can if you want, you don't have to. You're going to write enough down to have the confidence to go on in your problem solving. All right, on to the next part. I'm starting with hours and I want to get seconds. Do I either know how many hours are in a second or how many seconds are in an hour? Well, I could work that out, but it seems easier to start with how many minutes there are. I know that there are 60 seconds in a minute, and that means I could know how many seconds if I knew how many minutes. But I'm not back to hours yet, so I'm going to have to go back one step further. If I knew how many hours were in a minute or how many minutes were in an hour, which I do, I could do that. So now I've gone all the way from what I want to know back to what I have, and I'm ready to solve the problem. So here I go. The question says that I'm driving at 112 kilometers per hour. I'm breaking the speed limit, unfortunately. Now, when I have units of something per something else, that really implies a fraction. That's 112 kilometers per 1 hour. So to work my units better, I've written it more like a fraction in this case. You do what feels good to you. Okay, my first map tells me that I have to go from kilometers to meters. I want to get rid of kilometers, which are in the numerator. So I'm going to cancel them out by putting them in the denominator. I want to get meters. They go on the top. Units first. Don't jump for the numbers too soon. There are 1,000 meters in a kilometer. Kilometers in the numerator cancels kilometers in the denominator, and I'm left with meters. All right, on to the second part of the map. I didn't leave myself much room here. Let's continue on. I'm going to string these all together, but of course you could do them one at a time if you like. Now, I've got hours, and I want to get seconds. This time, hours are in the denominator, so I'm going to cancel them out by putting them in the numerator. And that means if hours are in the numerator, then the minutes have to go in the denominator. Units first, don't worry about the numbers. All right, now that I have the units, I can see what numbers. There are 60 minutes in 1 hour. Hours in the denominator cancels hours in the numerator. Good to go. So I'm left with meters per minute. Getting closer. Now this is getting complex. If I didn't have my map, I might be lost by now, but I'm not. I'm going to do the last step to get from minutes to seconds. Here's my conversion factor. Minutes are in the denominator here, so I'm going to cancel them out by putting minutes in the numerator. That means the seconds go in the denominator. And the units tell me what numbers to put. 1 minute is 60 seconds. Using this approach, you'll never make a mistake of, was I supposed to multiply by 60 or was I supposed to divide by 60? You'll know for sure. Minutes in the denominator cancel minutes in the numerator, and I'm left with meters per second, which is what I wanted. Woohoo! Doesn't guarantee I'm right, but sure feels better than if I hadn't gotten the right units. All right, you might want to pause and work this on your calculator. One nice thing about stringing the factors all together is that you're less likely to get round-off error. So 112 times 1,000 divided by 60 divided by 60. And how many significant figures do we want? My measured quantity has 3 significant figures, and I'm multiplying, so the rule is that I keep 3 significant figures. The other conversion factors are all exact. That's 31.1 meters per second. Now, novice students quite normally say to me, is this right? Is this right? It breaks my heart that the education system has beaten the confidence out of you. I don't want to be the way you know something is right. We want to have a strategy that tells us if it's right. So the most important reinforcement that we get from solving problems by dimensional analysis is, if your units worked out properly, the way they really do, not the way you want them to, then you're pretty sure you're right. In the previous example, we thought about the magnitude of the number and saw if that made sense. I think this one may be too complex to do that with. All right, on to the next example. And again, if you want to pause the video and try it yourself, you can do that now. I'm going to jump ahead. Now this question asks me to convert the density of mercury in grams per cubic centimeter to kilograms per cubic meter. Okay, so when you paused, you were making out your map. The question part of the question is to get kilograms and cubic meters, starting from grams and cubic centimeters. So for grams to kilograms, if I knew how many grams were in a kilogram, and I do, I could do that conversion in one step. If I didn't, I might have to insert another unit in between and do it stepwise, as we did from hours to seconds in the previous example. Now for the next step, if I knew how many cubic centimeters were in a cubic meter, then I could do it in one step. And actually, I don't just yet. You might think you do, but consider this. I know that there are 100 centimeters in 1 meter. Now, I don't want meters, I want cubic meters. So I'm going to cube the right side of the equation. And in math, I know that equal sign is taken very literally. Whatever I do to one side of the equation, I have to do to the other side of the equation. So 1 cubic meter is not 100 cubic centimeters. 1 cubic meter is 100 cubed, or 1,000,000 cubic centimeters. So keep that in mind as you work your conversion factors. And again, this time I showed more detail than I showed before. I show myself as much detail as I need to be clear enough to be confident in what I'm doing. If you need confidence, write something down. All right, so I know now how many cubic centimeters are in a cubic meter. I've closed in all the gaps and I'm ready to start my problem. So here we go. I start with 13.6 grams per 1 cubic centimeter. And here come my conversion factors. Maybe you want to pause here and continue on without me. I'm going to continue. My map says get rid of grams, which are in the numerator, so I'm going to put them in the denominator, and get kilograms. That goes in the numerator. Units first. They tell me what numbers to go get. There are 1,000 grams in 1 kilogram. And now I work the units like I'm not the one that provided them. All right, on to the next step. I have to get rid of cubic centimeters and get cubic meters. Now the centimeters are in the denominator over here. So that means I'm going to put the centimeters in the numerator to cancel it out, and the meters go there. I know that there are 100 centimeters in 1 meter, as I showed you above. But I also saw that I had to cube that to make my units work out correctly. So now when I expand that, that would be 1,000,000 cubic centimeters over 1 cubic meter. I wrote it like this. If you want to actually write out 1,000,000 cubic centimeters is 1 cubic meter, there's more than one way to skin a cat. Tell me any truth and you'll be fine. All right, so that should do it. The cubic centimeters in the denominator will cancel cubic centimeters in the numerator. That still applies here though. And I am left with kilograms per cubic meter. That's what I wanted. Woo! So now I'm going to grab my calculator. Well, maybe I'm not. You're allowed, and you might want to pause and do that. But what I see is I'm taking 13.6 times 100 cubed times 10 to the 6th, divide it by 1,000, 10 to the third. 10 to the 6th divided by 10 to the 3rd is 10 to the 3rd, or 1,000. Or in other words, 13.6 times 10 to the 3 kilograms per cubic meter, which is exponential notation, but to make it scientific notation, the decimal should be after the first number. (1.36 times 10 to the 4th kilograms per cubic meter. Now again, my units worked out. I can't tell if that's a reasonable number with these units. I just have to rely on the dimensional analysis. Units are my friends. Let's try one more. The sulfuric acid in a car battery has a density of 1.2 grams per cubic centimeter. What is the mass of 200 milliliters of this acid? So maybe you want to pause and try it by yourself. Remember, any clear solution is a good one. I can think of 2 ways to solve the problem. Here's first way is the way I'm not going to solve it. You might have memorized that density is mass over volume. And the reason I'm not going to use that approach is I hate memorizing things. I like to use my brain to think instead of memorize formulas. However, if you do remember this formula, you're allowed to use it. I will point out that units are your friends even if you chose to use that. Maybe you weren't sure whether density was mass over volume or volume over mass, but the units of the quantity tell you it's a unit of mass divided by a unit of volume, which reminds you, oh, it's mass over volume. Now, I'm not going to do it that way. I'm going to solve this problem by dimensional analysis because that means I don't have to think anymore. I don't need to memorize anymore. I certainly do have to think. So I'm going to go to my regular approach. The question part of the question is, what's the mass? And maybe we'll do that in grams. It doesn't specify. Whatever works is just fine. Now, what do I need to know that? I need a conversion factor that has grams in it. And what I see in the density is a quantity that has units of something per something else. Whenever I see that, I can write that as a conversion factor. That means 1.2 grams is a cubic centimeter of sulfuric acid. And now that I have the conversion factor, I can see if I want to find grams, I can find it if I know the volume in cubic centimeters. So let's see if we're done. Do I know how many cubic centimeters? Well, I don't. I know how many milliliters there are. But if I knew that conversion factor, I'd be all set. And we derived in an earlier lecture that a milliliter was the same thing as a cubic centimeter. So now I've got my conversion factors. I can go right ahead. The question says, start with how many milliliters? 200 decimal point milliliters. Don't throw away significant figures. They truly are significant. That decimal point means that I know the volume to the nearest 1 milliliter. All right, here comes my conversion factor. I want to get rid of milliliters. So that means the cubic centimeter goes in the top. And I'm left with cubic centimeters. If you had just wanted to say that 200 milliliters was 200 cubic centimeters, I'd probably buy that too. All right, so now we're at cubic centimeters. My map says in the next step, get rid of cubic centimeters and get grams. And again, units go first. Grams in the numerator, that's 1.2, is 1 cubic centimeter. Work your units like you're not the one that proposed them. And here we go. So when you work that out on your calculator to the correct number of significant figures, if you need to pause and do that. This is another one I can probably do in my head. I think that's 240 grams. Now let's make sure we got the right number of significant figures. I'm multiplying, so I care how many significant figures I have. There's a decimal point here, so the trailing zeros are significant. We've got 3 significant figures times an exact value times a measured quantity. Somebody measured that density to 2 significant figures. So I only trust it to 2 significant figures. That's 240 grams, no decimal point. That means I can only trust the mass to the nearest 10 grams. So you see, I didn't need to remember a formula. And that's a great thing. Sometimes people are intimidated to solve a problem if they think they can't remember something. You don't have to memorize things. Just be prepared to trust that you're going to be able to think it through with dimensional analysis. Now, sometimes I have a hard time convincing students that units are important even at the in-between stages in your question. You love units. They are powerful clues. You wouldn't want to get rid of them. In an earlier lecture, I listed off that measurements are meaningless without units, and I'm sure if I asked you to memorize those things, you'd parrot them back to me. But what I really need to do is to put a unit with every quantity. And let me tell you a cautionary tale that shows the problem when somebody didn't. This is a picture of the Gimli glider, which was an airplane that left from Montreal heading to Edmonton back in 1983. That date is going to turn out to be important. What happened is they were heading to Edmonton from Montreal, but they got over Gimli, Manitoba and ran out of fuel. And the pilot successfully made a safe landing on a racetrack, a car racetrack. So all wells that end well. But here's what went wrong. I told you this was in 1983, and I remember it well. That's when the metric system came into Canada. What happened was that the fuel gauge on the plane wasn't working, And you can fly without the fuel gauge as long as the mechanics measure the fuel in the fuel tanks with a dipstick. So they measured the depth of the fuel in the tanks and converted that to liters that way they had on board. What they knew were how many kilograms they needed to go that whole distance. So they knew they needed this many kilograms in total. So they needed to convert from liters to kilograms, and one of the guys yelled to the other guy, "What's the conversion factor?" And somebody yelled back 1.77, but didn't put any units on it. So when they worked it out, they worked out that they needed to add only about 5,000 liters of fuel, when really they needed 4 times that much. Here's the problem. The units on that number that they didn't show were pounds per liter, because in the old days before the metric system, people used pounds. But it should have been kilograms per liter. And what is often true, that when you change the unit, you change the numerical value as well. So all's well that ended well with the Gimli glider, but you are always going to show units clearly with your conversion factors to help your reader follow your logic and to keep you safe.